Okay, folks, welcome back to regression analysis. In the previous lectures, we introduced what simple regression and multiple regression are, and we went ahead to talk about some estimation methods, the ordinary least squares, and maximum likelihood. Okay, and then we did some derivations and so on. In this lecture, we are going to talk about inferencing, okay? So, you have specified your model and you have run your model. And a lot of the times we have a reason why we are running regression models. Okay, so usually you'll be interested in the overall performance of the model. Okay, remember you are trying to explain variations in Y using variations in your X variable. So did your X's do a good job, okay, in predicting changes in the Y or not? That is what we call the overall adequacy of the model, okay? And then you want to see which regressors are important in our returns to schooling example. For example, you want to see whether experience was important in explaining differences in wages, was education important, or tenure important as a variable. Okay, so two things: the overall adequacy, was your model useful or not, and which regressors appear to be important. Okay, so statistical inference, okay, that we do in regression analysis are basically called the confidence interval and hypothesis testing about population parameters. Okay, so before then, as you know, most of the tests, T, F, chi-square, all of them stem from the normal distributions, and therefore we must begin to think about making additional assumptions about our error term before we can apply the familiar tests that we know for inferencing in statistics as an applied field. Okay, so we make assumptions about the errors. We assume the errors are normally distributed. That allows us to use some of the familiar tests, like I said, chi-square, sorry, the F test, the T test, and so on. But do we just make this assumption in a vacuum? Not necessarily. Anyway, before then, once you make the assumptions that the errors are normally distributed, it's a picture showing normal distributions. And then if you thought of Y to be beta 0 plus, if you thought of Y to be beta 0 plus beta 1 x1 all the way beta k xk plus our error term, then if you take expectation of Y, okay, condition on X, then this is the only one that gets to have the expectation operate on it, right? And we assume this is 0, remember. So it should be clear to you why the expectation of Y condition on X has such a mean. And already you know the variance is sigma squared, okay? So if U or the error term is normally distributed, this is how Y also tends to be distributed, okay? So like I said, we don't just assume the errors are normally distributed just for assumption's sake, but there is some reason to believe it could be true. Okay, the error term is a sum of many different unobserved things. And if you sum many independent factors, like if you are really many, then the central limit theorem says it doesn't matter the distribution you begin with. As the sample size increases, we approach the normal distribution. Okay, so there are some discussions. How many are these unobserved factors? Are they many enough? Are they independent? But the good news is, as long as we have a sizably good sample, a huge sample, then we rely on the central limit theorem and say our errors or data is normally distributed. Okay, so the normality is not difficult to attain once you have a huge sample size, and that's why we always stress that you should have a good amount of sample. I think in basic statistics, they talk about 30 as minimum and so on. For some study, you have no option than to use all the data available, and it might not be enough. Some of them, like if you are downloading inflation data, we have that for several years. If you want data you are collecting, you can increase sample size and have many more people in the study so that the normal assumption is not violated. Okay, so one more thing to say here, that we basically rely on the sample size. Even if we think the data is not normally distributed, there are certain things we can do. For example, we can take the logarithm of wage instead of just using wage. And we will see some useful transformations later in the course, which when we realize our data or errors are not normally distributed, we'll be able to correct that, okay? So remember, I may be saying errors are normally all the data because I've shown here that once the errors are normally distributed, then Y also follows similarly, okay? Okay, so we want to do inferences. Over here, we assume our errors are normally distributed, and for that matter, our betas, which are functions of the data, are also normally distributed. Beta here is normally distributed with mean, the true parameter, and this is the variance. And as usual, when we do this transformation, they become the standard normal with mean 0 and variance equal to 1. Okay, so that's what we call the normal sampling assumption. Okay, so this is where the work begins, my dear friends. Okay, we want to pay attention here. We want to test the overall significance of the regression. Okay, so regression has been run. Some X's or predictors or regressors were used. We want to see the overall significance. Taken together, does this regression give any advantage over just using an intercept to predict Y? Okay, using the regressors all together, was it useful? Did it make any difference? Okay, so the null hypothesis is, okay, that the explanatory variables are not useful. If we set all of them to 0 in the null hypothesis, we are saying they are completely useless. And because we are setting all to 0, in other words, all this, we don't need them. We could have just estimated Y using its average or something, okay? And the null hypothesis says, no, at least one of these X's is useful, okay? At least one of the X's. So H1 is beta J is not 0 for at least one of the J's. Remember, J's goes from 1 to K, okay? So once you set all this to 0, if all these go to 0, okay? By the way, this is called a full model. Full or unrestricted. Please remember this. You must know what a full model is, or you must know what an unrestricted model is. This becomes a restricted model. It's restricted. Over here, the null hypothesis has been imposed. In other words, all these have been set to 0, and therefore we are left with Y is not different from beta 0 plus U. It is the restricted model. Okay, restricted here is restricted. Of course, look at how it looks smaller. Okay, it's restricted. Another name is what? Modified. You must know the difference. Okay, so this is the F statistic we are going to use to test the overall significance, okay, of the model. Okay, let me make a correction here. I prefer to put Q here. I prefer to put Q here, and you will soon see why it makes things easier. Okay, so let's go. Let's continue. So over here, the F statistics is set up so that if the F is big enough, we reject, okay, H naught. If F is big enough compared to the critical value, we reject the H naught and say no, at least one of the regressors is actually useful. Okay. Now, first of all, you should appreciate that the small r here is restricted. SSR restricted from this model, and UR is unrestricted coming from this model. Q is the number of restrictions. So let's count them. 1, 2, 3, 4, 5, all the way up to K. Okay, so the number of restrictions Q is K. Okay, so these are the restrictions. Beta 1 equals to 0. Beta 2 equal to 0. All of them individually are being set to 0, including beta K. And so when you count them, there are K of them. They've just been written on one line, but you should be able to count that our restrictions Q equals to K. That's the number of restrictions. So this is error sum of squares unrestricted, error sum of squares restricted, N is the sample size, K is the number of regressors, not parameters, regressors. There is another form we can write this, okay? You should be able to convince yourself, show mathematically that this is equal to that, okay? Remember our definition of R squared, all right? If you know the definition of R squared, you can create it from here. You divide these things by SST. This one by SST, by SST, by SST, and play them around. Okay, I challenge you, manipulate and get this. So in an exams, if you are not provided with this information and you are provided with the R square, the restrictions, regressors, you should be able to compute the F statistic. Okay, there is another way we can write. So all these three are useful. Okay, if you are going to an exam, you must know all the three. This is R squared run from the unrestricted model, R squared from the restricted model, and so on and so forth. Okay, now the test makes sense, right? The F statistics makes sense. We expect this F to be positive, as F is always positive. In other words, this guy is always bigger than this guy. Think about it, right? SST is how much you're able to explain and how much you couldn't explain. If you have no regressors at all, this one will be very small and this one will be very high. As compared to here, there's the unrestricted model, right? Because the regressors come in to explain this part. They fetch away from this guy. So as long as you have no regressor here, then this guy is going to be very, very high. Actually, this guy is supposed to be 0 because there are no regressors. So it should be clear why this guy is bigger than this guy. So if you are going to be rejecting H naught, then this should do a good, this should be, if you are going to be rejecting H naught, the regressors should explain a lot here. Once they explain a lot here, this SSE of the unrestricted model will become smaller, because if this is increasing, this must be decreasing. So as this increases, because your regressors are doing a very good job, of course, obviously this guy must be falling. If it's falling here, then this one must be going up, because this is like the useless model has no regressors. So each error term is huge. So it will be bigger than this guy, and then the F becomes big. Therefore, you can reject H naught. Okay, you are rejecting H naught, and no, at least one of my regressors is useful. Okay, so that's how the F is set up, so that it will be able to have the ability to reject H naught when it should. Okay, and so on. Okay, let's go on. So this test is similar to analysis of variance, where we divide regression sum of squared by the error sum of squared to get our F statistics, which you have done before. Okay, and how do we get the sum of squares regression? It has K degrees of freedom. Okay, and then, by the way, K is the number of regressors. Okay, and then we have the error having N minus K minus 1 degrees of freedom. Okay, it is argued that the SST begins like this, right? It begins like this. SST, I beg your pardon. SST begins like this. I equals to 1 to n. Okay, but there is a restriction on this, which says when you sum y minus y bar, it goes to 0 by itself. Okay, so once you are looking for your SST, there is a restriction you keep in mind, only one of them. Okay, so because of that, this cannot have n degrees of freedom. Okay, because there's one restriction it must obey all the time, so it loses 1 degree of freedom, this guy. That is why it becomes n minus 1. And then you remember our normal equations when we're doing simple regression. We had some 2 normal equations, which is, if I remember correctly, there was -2 somewhere here. We had y minus beta 0 minus beta 1x equals to 0 for the first one. The other one, we had this y minus beta 0 minus beta 1x, and there was x attached equal to 0, remember? And what is in the bracket is just what? So it's pretty much like summing to u hat. If we put a hat, on the estimators, so this becomes u hat. This is 2, right? -2 equals to 0, and then negative summation of 2, it was u hat x. Okay, because what's in the bracket is like u hat. Okay, so here also we can have taken from the first one alone. Okay, I equals to 1 to n. You are summing u hat equals to 0. So the idea here is that SSE itself looks like this: y minus y hat squared equals to 0, but y minus y hat okay, so let's continue. So over here, right, y minus y hat also, this is also sums to 0. I equals to 1 to n, but basically you have n independent data points. Remember, degree of freedom could be defined as the number of independent pieces of information, okay, calculated statistics or something. So we have n data points, but we have k plus 1 equations. Okay, in simple regression, we had equation 1, equation 2. Do you get me? So the degree of freedom here, if you remember from your elementary class, would be n minus 2 over here. There was equation 1, equation 2. Here also in multiple regression, there will be an equation for beta 0 hat all the way to beta k. Equations for all of them that you differentiate with respect to beta 0, differentiate with respect to beta, all the way to beta k. So you're going to have like k plus 1 equations to respect or obey. These are like restrictions. So that's how I can explain to you why out of n data point we lose k plus 1 degrees of freedom. Okay, and degree of freedom too can be interpreted as the complete minimum information needed to specify a test statistic, okay, or a parameter. It turns out that if you have beta 0, then immediately you know beta 1. Remember, beta 0 hat was y bar minus beta 1 hat x bar. I'm just teaching you simple regression related to multiple. So immediately I know this guy, then I know the other one, and vice versa. Okay, so although there are kind of k plus 1 parameters, if you know k of them, you'll be able to recover the beta vector. Okay, so this also gives us an idea of the degrees of freedom here. Of course, if you just know, if you understand these two, then this minus that, you get this. They should add up. This plus this should get to this. Okay, so that's the idea. You are statistician. I'm sure you are fine with degree of freedom. I just wanted to throw some light. But remember them, this is the number of regressors, not parameters. Some books use parameters here. They are counting from beta 0. So they may have different numbers here from I2, but K is the number of regressors for me. Okay. So basically, to test, what we just saw was a test of the overall significance, the model adequacy. So over here, to be able to test individual, okay, regressors. So you take their coefficient and test whether beta j is 0 or not, okay, an individual one. And we construct our t-statistic by putting the estimated value over the standard error of that value, okay? And this, we've seen it before earlier lectures where we derive the variance or covariance of the big matrix. Okay, remember from your notes is sigma squared x transpose x inverse. So if you are looking for an individual j, then you are going to pick the diagonal column from this matrix. Okay, and our usual t rules hold. If absolute value of t statistic is greater than t alpha over 2 for a two-tailed test, okay, like this, then you reject h naught. If not, we'll practice some of this. I have a good example which will tidy up everything and clear things in your mind, okay? So this is our usual t statistics beta hat over its standard error is t distributed with n minus k minus 1 degree of freedom. And I think in this class, we are going to be using 5% alpha level. Okay, now the hypothesis I just showed you assumes something like beta j null hypothesis equals to 0. But more generally, you may not have 0 here. So more generally, if you have a value here, then you just take the estimate minus the hypothesized value. Over there, the previous line, hypothesized value was 0. So we always put 0 here and actually never wrote it. We just wrote beta j hat over its standard error because putting minus 0 is trivial. But this time, if it must be a number other than 0, please put it there. Okay. Okay, so the test works exactly as before. Okay, let's take an example here. Okay, so we have, okay, I actually didn't show you how to interpret the logarithm once. Maybe in one of the videos I will show you, or even perhaps here. Okay, so here you interpret them as elasticities. The economic student will appreciate this more, but it says that when enrollment increased by 1%, crime will increase by 1.27%. Okay, don't talk about the log. When it is log, then a percentage change in this variable leads to this 1.27% change in the crime variable. Okay, now I would derive the explanations later on. Okay, but for now, let's learn how to do inference and test. Okay, but here I said a percentage change in enrollment leads to 1.2% percentage change in crime. Okay, so we are going to test whether the coefficient on log enrollment, this is enrollment, okay, does, when students enroll in school, does it increase crime or reduce crime? That's what this regression is trying to study. We have our R squared sample size. Okay, this may confuse you, but it is just saying the coefficient on the enroll variable. Okay, so some people believe it must be 1 in the population. In other words, if enrollment increased by 1%, then crime will also change by 1%. Okay, hopefully to decrease. Okay, or whether when there are more enrollments, there is more crime. In that case, it will be positive. Enrollment going up by 1%, crime going up by 1%, and so on. So we test this is equal to 1 against that is not equal to 1. What's our t statistic? The estimate minus the hypothesized value It is estimated to be 1.27, hypothesized to be 1 over its standard error. So when the regression is presented this way, by the way, the number underneath here, some of you be aware already, is the standard error. So always remember how to calculate your t. If you do this mathematics, you get 2.45. And if you were to read t, okay, alpha over 2, 0.05 alpha over 2 against n minus k minus 1 degrees of freedom on the t table, okay, 2 tail test, this becomes 0.05. What is my n? N is given the question as 97, n here, minus k. K is the number of regressors. There's only one regressor. Only one regressor, n minus k minus 1. So you read, this is 95 then, right? Read this on the t table. You get 1.96. Actually, this is a number is familiar for t alpha, which is 0.05. Okay, you get 1.96. So since t calculated is greater than t critical, this is read from the table. I know this is a familiar number to you. We reject H naught. Okay, we reject H naught. The hypothesis that this coefficient should be 1 is rejected. So when enrollment increases, crime actually increases by more than 1%. Okay. I hope that is clear. You should practice these things, not just watch the video and go. Take your calculator and also check them out, okay? So on these slides, we are going to test multiple linear restrictions, okay? Earlier on, we tested overall significance, all the beta 1, all the way up to beta k was 0. This time we are going to take subsets, okay? Just subsets, not all of them, okay? Multiple restrictions. Okay, later on we'll study a generalized form of doing these things. But for the purpose of this lecture, we are going to be taking some restrictions, not all of them. Okay, so this is an equation of salaries of baseball players on some variables. These are the years in the league, average number of games they play per year, batting average, home runs per year. These are performance indicators, okay? You don't need to understand these variables to answer the question, okay? Those who know baseball will understand. Now, this is what we want to test. We are not testing all beta 1 up to beta 5. No, just a subset, okay? We are hypothesizing that all the performance measures are useless. They are not useful in predicting the salary of a baseball player. So we hypothesize that this is 0, beta 4 is 0, beta 5 is 0. And H1 says no, H naught is not true. So at least one of these, we are saying 1, 2, 3, at least one of them is useful and it's not 0. Okay. As usual, the unrestricted model is estimated for us here. Okay, this is the unrestricted model. Everything here, when you run it, is unrestricted. The restricted model will plug in 0 here, 0, 0. So this here becomes the restricted model. Something like this. It's restricted after you impose this condition that all the beta 3, beta 4, beta 5 are 0. Then you have what? The restricted model. So if you run this, just this one, then you've run a restricted model. But if you run everything, there is a full model or unrestricted. That has been run for us here generously, and we have the standard errors. We have n SSE r squared. Okay, now we need the restricted model also run for us. This is the restricted model. Remember, the unrestricted is the full model. It has all the regressors, 1, 2, 3, 4, 5. But look at the restricted. Once we impose those conditions, you have what? 1, 2. Okay, only 2 regressors. The other 3 were hypothesized to be 0. So this is what the restricted model. And this is the SSE associated with that, and the R squared. The sample size is the same. Remember our F statistics, always SSE restricted, SSE unrestricted. So what number goes here? SSE restricted, this one, because it's from the restricted model. What goes here? The SSE from the previous slide, because that's the unrestricted. Let me go back. It is here. This is the unrestricted, the full model. So this number goes right there. What is our Q? Q is the number of restrictions, right? Let's count Q. Q is here. Number of restrictions from the H0 you can count. Here we are. Q is the number of restrictions. Q, number of restrictions. There's 1, 2, 3. Q is equal to 3. Our N is what? N. We will see that here. Here we go. Here we go. So here we are. This is SSE from the restricted model. SSE unrestricted. Q is the number of restrictions. This is N, sample size. N minus K. K is the number of regressors in the full model. There were 5 of them. N minus K minus 1. If you compute this with a calculator, you get 9.55. So you are supposed to read F with Q, N minus K minus 1 degrees of freedom on the F table. That is F 3. What is N minus K? That is 347, right? If you do 350, 3 minus 5 minus 1, it should be 347. So this is what you read on the F table. When you read that at 1%, you get 3.78. So since F calculated here, 9.55, is greater than F critical, we reject H0. So we reject H0, so the 3 variables are jointly significant. If you reject H0, you must give an interpretation that all those 3 variables are jointly significant. Remember, H0 said they were useless. They were all 0. We have rejected H0, so they are jointly significant. You must know your decision rule. You reject appropriately, correctly, fail to reject correctly, and interpret what it means. Here, it means the 3 regressors are jointly. Remember, F test is a joint test. Okay, it's the T test, which is individual test. So they are jointly significant. Okay, now there's a statement here which says they were not significant when tested individually. Okay, let's check that and see whether it's true. Okay, they were not significant when tested individually. So let me get my calculator. When you test individually, for example, this one, individual test is T. Joint test is F, so T. What is the estimate? 0.0108 minus the hypothesized value of 0, so it doesn't matter. This is 0.0, and standard error 0.0072. What is it? Take your calculator. I'm looking for my calculator right now. I don't know if you can see, but I'm punching in here. You should also punch. I have 0.0108 divided by 0.0072, which is equal to, I got 1.5. I got 1.5. You can also confirm. I got 1.5. So I'm just checking one of them. I got 1.5. 1.5. This is my T calculated. Remember, T critical, when you read from the table at 5%, will be 1.96. So T calculated is less than T critical, so you fail to reject H0. Fail to reject H naught, and conclude. Remember, this is H naught. It's saying this particular beta 5. Remember, this is beta 1, beta 0, beta 1, beta 2, beta 3, beta 4, beta 5. This thing here is what we are rejecting. We are failing to reject. Okay, T calculated wasn't bigger than T critical, so we failed to reject this guy. Once you fail to reject, you are accepting that it is 0, in quote, accept. Of course, anything which is 0 is not significant. If your salary is 0, that means your salary is not significant. So when we fail to reject, we say beta 5, or the variable associated with it, RBISYR, is not significant. It's not significant. It's important you reject or fail to reject appropriately and give interpretations. If we had rejected, it would have meant it is significant. So please note that if you reject something like this, right, this is saying it is 0. If you reject this, you are saying it is not 0. Once it is not 0, then it's significant. If, however, you fail to reject, you are, in quote, accepting is 0. And if something is 0, just keep in mind that it is not significant, right? Like I said, if your salary is 0, it's not significant. Okay, it's not something you are proud of. Okay, so I've shown you an F statistic which shows a joint significance of more than one variable, and a t-test for a single test, okay, of one variable or parameter. Okay. Then, so I've shown you that, and you can confirm, I have just done that beta 5 equals to 0 cannot be rejected. You can do same for beta 4 and beta 3. That is the statement here, that they were not significant when tested individually, but the 3 were jointly significant, as we have shown here. What does that suggest? There's likely to be multicollinearity, that the 3 regressors are likely to be highly related. These 3 are likely to be highly related. 1, 2, 3. Therefore, individually, they are not strong, right? Once this is in a regression, it weakens the strength of this guy and this guy, because this guy is representing both of them. If this is also here, these two may not be strong, may not be significant, because this is representing them, and so on. That is why individually they may not be significant, but all together they show the same thing. They represent the same information. So jointly they will be significant. So that's symptomatic of multicollinearity, which we have explained to be where the regressors are highly linearly related. Okay, let's try another test inference. Okay, let's try another one. Over here, okay, it's just a practice. So the regression has been given over here. Okay, I will show you how to interpret log, and so on in tutorial when I give the third practice set of questions. Okay, the third set of questions. I've sent first to which will be homework. The third one is likely to be practice, and that one I will derive and show you the interpretations, okay, of the logarithm and so on. But first of all, let us test some restrictions. So we are claiming that beta 1 is 0. In other words, send this should not be here. Beta 2 is 0, this should not be here. That is if we accept this. Beta 3 is 0, and beta 4. Oh, okay. So this is testing that all of them are 0, but there is a trick. This one is not 0, so it is not our usual overall significance. Okay, this one is 1. So you can be asked to test anything. Okay, this one is 1. This assessment is like when the value, there's a value placed on your house versus how much it actually sells for. Maybe it's valued for $100,000 and it sells for 120. So this is like assessment if the house is assessed, okay, and a price quoted. for it. This is the square feet of the bedrooms. This is the number of bedroom and the space, okay, in the house. We want to see whether beta 1 is equal to 1 and every other thing doesn't matter. 0, 0, 0. That is it. Okay. Now, let's write, this is our full model. This is our full model. Let's write down the restricted model. Restricted model, you impose this condition. So if I ask you in an exam to write down the restricted model, impose this. Wherever you see beta 1, put 1 there. Okay. Wherever you see beta 0, put 0 there. Sorry, wherever you see beta 1, put 1 there. Like here, put 1 here. To write a restricted model, you impose the condition. Wherever you see beta 2, put 0. So if you put 0 here, that will take this off. Wherever you see beta 3, put 0. So you put 0 here, it knocks this off. Wherever you see beta 4, put 0. It also knocks this off. So we are left with what? Our y. Okay, I don't want to be writing long sentences. That's why I'm writing y. And we are left with beta 0, something like that. We are left with here. This is our plus. Remember, we put 1 here. So beta 1 doesn't exist anymore. So plus 1 x. Oh, yes. Log x. That's all. Plus u. Okay, try it. This goes to 0, 0, 0. They have y equals to beta 0 plus 1 times log x. This is our x1 or something. Okay. On the next slide, you will see it. So here we are. We have represented all those ugly names. Look here. So this is what? X1, X2, X3, X4. Oh, what do I have here? Yeah, X1, X2, X3, X4, and beta 0. So this looks like our full model or unrestricted. If we impose that condition, this is our y, beta 0. We were told to put 1 wherever we see beta 1. So this becomes coefficient of 1. This goes to 0 because we were told to put beta 2, 0, beta 3, 0, beta 4, 0. In the H0, okay, on the previous slide, we were to set all this to 0 to get our restricted model. Okay, so this is the restricted model. This is the restricted model. And we can do some algebra, okay? Remember, this has no coefficient anymore, so it cannot stay on the right-hand side. So we transfer it to the left-hand side and leave this on the right-hand side. That's it. We can actually rewrite this. Our y is now looking like something else, which we can give a name to it as y star is beta 0 plus u. So you now have a new dependent variable, which is y minus x1. Anyway, this is the regression. I don't think I show all the details, but when you run them, which we will do in a practice exercise, you will have SSE restricted, provided, unrestricted, also provided. Just plug in the numbers. Q is the number of restrictions. Let's go and count the number of restrictions. Number of restrictions, 1, 2, 3, 4. Okay, number of restrictions, 1, 2, 3, 4. So Q is 4. Okay, Q is 4. Q is 4. Number of restrictions, Q. So N minus K minus 1. If all the numbers were provided, I'm sure you can fill this in. I provide some on the next slide. I don't provide some. But the F calculator, you don't need to know what is this. The input is what the conclusion. We got this. And if you read this F calculated, this is F critical from the table, which is going to be what? F Q N minus K minus 1. You get 2.5. Okay, at 5% significance level. So F calculated is less than F critical. So we fail to reject. Okay, we fail to reject. Okay. And conclude that the H1 might be true, that this one is 1. We fail to reject. That means this is actually the model we are dealing with. Okay, and not the full model. Okay, so this is the regression that was used in the previous slide. This is from unrestricted regression. So you can see where this number came from. That was plugged in. You can see our N, and K is the number of regressors, right? 1, 2, 3, 4. Okay. So in all these tests are valid based on our assumptions that our errors have 0 mean, there is homoscedasticity, the 0 conditional mean, the errors are normally distributed. Actually, if you're asked in an interview, why do we assume the errors are normally distributed in a regression? It is only meant for hypothesis testing or inference. We don't need that assumption to say our estimates are blue. Remember, we said our estimators are blue, Bayes linear unbiased estimators. Yes, you don't need the assumption that the errors are normally distributed to get this. But in addition, when we bring on board that the errors are normally distributed, what is its purpose? For inference and hypothesis testing, confidence interval, and so on. So if you go for an interview, remember that. Okay, remember that. Okay, so we assume the homoscedasticity, 0 conditional mean, or error having 0 mean, errors are normally distributed, there's no perfect collinearity. All those assumptions are needed to make our test valid. Okay, we are using a t-test which relies on the normal distribution. So those assumptions cannot be taken for granted. Okay. Okay. So, okay, so I'll stop the video here and then continue in the next lecture. Okay. I hope you are following and work through these things. Okay. Catch you on the next video. Bye.